Alright, so looking at our do now here, we have a experiment here where we've done 50 trials to draw out of a bag. We've got these number cubes in here, or these colored cubes in here. First, we're going to need to find the probability so we can then use the probability to answer the questions below. So looking at this, our probabilities 12 out of 50, 18 out of 50, 8 out of 50, and 12 out of 50. It's going to give me 0.24, 0.16, 0.36, and 0.24. Coming down here, it says how many more draws would you need to make in order to get 50 green cubes. So 50 green cubes, that's a quantity, and our quantity equals percent times whole because that's the part. We're looking for the whole number of trials. So we get 50 is equal to, and then we're talking about green cubes, so probability would be 0.16 times our unknown whole, divided by 0.16, divided by 0.16. We get that the whole is equal to 312.5, so rounded, we would expect it to be approximately 313 draws. How many red cubes? So it's asking for a specific, so the Q is going to be the unknown. Would you expect to draw from a bag? If you were to draw from the bag 225 times, so that's our whole number of trials. And we're talking about probability of red, so that's 0.36 times 225. And that gives us exactly 81 red cubes. All right, let's flip on over and look at our aim for today. All right, today's aim, Kipsters will be able to describe and use simulations for probabilistic events. All right, so in previous lessons, we estimated the probabilities by collecting data empirically. That means we went through and we did trials, or we've also done it by establishing theoretical probability models. So there are real problems for which these methods may be difficult or practical to use, and so we use simulations. And the simulation is a procedure that will allow us to answer questions about real problems by running experiments that resemble the real situation. So we're thinking about real-world situations where we're going to create a probabilistic event that we think will have similar probabilities, so we can kind of get the idea. It's often important to know the probabilities of real-life events that may not have known theoretical probabilities. Scientists, engineers, mathematicians design simulations all the time to answer questions. I think about one thing that I do is I read a weather blog where it talks a lot about kind of weather predictions, and a lot of weather predictions are really just places where they've taken weather patterns from the past and they've created those things. So we can see here, looking at these simulations, answer questions that involve topics such as diseases, water flow, climate changes, functions of an engine. These are all things that we simulate because they do have some random occurrence. Results from the simulations are often used to estimate the probabilities that help researchers understand the problems and provide possible solutions to the problems. So, our first situation is, how likely is it that a family with 3 children has all boys or all girls? Alright, so let's assume that it's equally likely for a boy or a girl to happen. Instead of observing the actual results of births, because this could take a long time if you're waiting for a bunch of people to have a birth. You could use a simulation for this, and the simulation could be that you could toss a fair coin to simulate the birth. Again, we'd use tossing a fair coin because it would have something close to an equivalent probability, since we think boy and girl would be approximately the same. If the result, we could set it up so if the toss was a heads, that was a boy. If we tossed the tails, then that was a girl. If the coin is fair, then getting a boy or girl would be equally likely. So suppose a family wants to have children. To simulate the genders of the 3 children, they toss a fair coin, or they could roll a number cube. That would be used 3 times, and once for each child. For example, 3 tosses of a coin could result in heads, heads, tails, and as we talked about those relationships earlier, representing a family with 2 boys and 1 girl. Or heads, tails, heads would also be 2 boys and a girl. Tails, heads, heads would also be 2 boys and a girl. They would just have different orders of those births. Alright, so suppose a prime number is rolled on the number cube and it simulates a boy's birth, and a non-prime number simulates a girl's birth. Using such a number cube, list the outcomes that would simulate a boy birth and those that would simulate a girl birth. Alright, and are the outcomes equally likely? So, basically, it's asking us here to define the sample space that represent a boy and a girl. So, the probability of a boy would have the sample space of all of the prime numbers. So, if we're going through and we're thinking about the prime numbers, we're looking at a number cube that's going to have 1, 2, 3, 4, 5, or 6. Our prime numbers are the 2, the 3, and the 5. So our possible outcomes here, this would be, and then for the girl, it'd be 1, 4, or 6. These are our non-prime numbers. So the question is, would they be equally likely? You should be able to answer that for yourself. Yes, this is 3 out of the 6 outcomes. This is also 3 out of the 6 outcomes. So yes, they are equally likely. Alright, suppose that one card is drawn from a regular deck of cards. A red card simulates a boy birth, and a black card simulates a girl birth. Describe how a family of 3 children could be simulated. In other words, give me a couple of quick sentences about maybe an example of what could be drawn and what that would result in. So you could write down any number of things here along the lines of, well, you could draw 3 cards, and if you had a black card, or if you got 3 black cards, that would be 3 girls. If you got 3 red cards, that would be 3 boys. If you got 2 reds and a black, this is just another way that we can simulate it. We can assume that those simulations would be accurate, as there are an equal number of red cards and black cards. Alright, so what we talk about here, simulation really just provides an estimate for the probability that a family of 3 would have 3 boys or 3 girls by performing 3 tosses of a fair coin. Each sequence of 3 tosses would be called a trial, and the trial, if a trial's result was heads, 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 or tails, 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 then the trial represents all boys or all girls, which is the event that we are interested in here. If the trial lands that way, then we would call it a success. If the trial results in any other result, then we would call it a failure. So the estimated probability that a family has 3 boys or 3 girls based on the simulation is a number of successes divided by the number of trials. So for instance, if we did this trial 100 times and in those 100 times, 28 resulted in heads, 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 or tails, 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 then our estimated probability that a family would have 3 children that were all the same gender, 3 boys or 3 girls, would be 28 over 100, or 0.28. So looking at the trials below, it says find the estimate that a probability will have 3 children that are exactly one girl, will have exactly one girl using the following outcomes. So we've done the simulation here. We've flipped a coin in sets of 3 50 times. So we've done 50 trials. So now we need to figure out how many of those trials represented the situation that we were looking for. If you go back, the situation we're looking for, our successes are going to be ones that have exactly one girl. Alright, so go through and start by circling all of the successes, and then go ahead and write a fraction to represent the probability based on this simulation. So based on this simulation, I've circled all of the successes based on this trial. I see that there are 10. So 10 out of the 50 trials would be successes, so we'd get 0.20 or 20% probability that you would have exactly one girl. So again, this is a simulation where we have modeled this using a probabilistic event that mirrors what we see in real life. So let's flip on over and look at a couple more examples. Alright, so in the second one, we're going to perform a simulation of 50 trials by rolling a fair number cube in order to find an estimate of the probability that a family with 3 children will have exactly one girl. Specify what outcomes of one roll of a fair number cube will represent a boy and what outcomes will represent a girl. So again, when we're looking at this, we want to think about this question. If we're thinking about modeling this correctly, we would assume that when we roll the number cube, we would want the outcomes to be equal. So how can we set up outcomes such that they would be equal when we're using a number cube? This is going to be different than a coin, because a coin there's only 2 sides. So we have to think a little bit more carefully if we're going to use a number cube. What number cube outcomes would represent boy and girl? So go ahead and make a list based on number cube outcomes. What are you going to say is a boy and a girl? So here we're kind of talking about designing a simulation here. So really you could have said whatever you want. You could have said boy is even, girl is odd. You could have said boy is 1, 2, 3, girl is 4, 5, 6. Doesn't really matter as long as you pick something where they're going to have even probability. So we saw earlier another example would have been you could have done prime and non-prime numbers, or prime and composite numbers. Alright, simulate 50 trials keeping in mind that one trial requires 3 rolls of the number cube. List the results of your 50 trials. So here I don't necessarily want you to list the results of your 50 trials in terms of actually listing it out. So I'm going to actually ask you to go ahead and do this in terms of a table. I really just want you to, and that's not going to be a very useful table. Try this one more time. Just list your number of successes and failures. So what we're looking for here, we're looking for exactly one girl. So when you do your successes, when you do your set of 3 rolls, then you want to go ahead and look for something that has an exact probability, has an exact outcome where there is one boy or one girl. Just depending on how you set this up. Again, you're referring back to this and your sets of 3. Once you've done that, calculate your estimated probability. All right, so hopefully you and your partner have gone through and your number cube. So maybe you got something out of your 50 trials, you got 23 successes and 27 failures. So the probability would be 23 successes over 50 would be 0.56. Now, obviously, I didn't actually do this, so my numbers should be significantly different than yours probably. It's all about thinking through this work as doing the simulation and create it. All right, calculate the theoretical probability that a family with 3 children will have exactly 1 girl. All right, so here let's go ahead and create to do the theoretical probability, we need to do this kind of the way that we used to. Thinking about this as a tree diagram and thinking about our possible outcomes. We have girl, boy. Off of that we can have a girl, boy, girl, boy, girl, boy. Same thing here, girl, boy, girl, boy, girl, boy. And as we follow our outcomes, we have girl, 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 boy, girl, boy, girl, girl, boy, boy. Off of our boy starting outcomes, we have boy, girl, girl, boy, girl, boy, 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 girl, and boy, boy, boy. So looking at this, our total probability so these are all of our outcomes. So assuming that having a boy and having a girl are equally likely, calculate the theoretical probability that a family with 3 children will have exactly 1 girl. So now we're looking for exactly 1 girl. As we go through here, this meets the criteria and this meets the criteria. So that would be 2 out of 8, which would be 0.25 or 25%. So compare that to the estimated probabilities found in Part A and Part B above. So that means we're actually going back to Part A and Part B of question 2 here. What did we find was the probabilities? And we can see that if my answer was here 56%, that would be significantly different. My guess is that when you look at yours, you're going to find that it's much more close. That you probably got something along the within 5 to 10%. All right. So we're going to do one more simulation. It says suppose that on average a basketball player makes about 3 out of every 4 shots. In other words, she has 75% chance of making each foul shot she takes. Since a coin toss produces equally likely outcomes, it could not be used to simulation for this because there's just not enough results. There's not enough outcomes. So instead we could use a number cube by specifying that numbers 1, 2, 3 would be a hit or a made shot, and the number 4 represents a miss. If we roll a 5 or 6, we're just going to pretend like that never happened, and we'll roll again. So based on 50 trials of rolling a fair number cube, find the estimated probability that she makes 5 or 6 of the 6 foul shots. So we're looking for any of these sets of 6 where it would show she made 5 or more of the shots. And again, going back to the way the simulation was designed, it's designed the simulation so that numbers 1, 2, or 3 would be a make and 4 would be a miss. So they designed it that way, again, because they wanted 75% or 3 out of 4 outcomes to be correct. So go through, look through this simulation, and determine how many successes and how many failures, and then determine the probability that she makes 5 or 6 of the 6 shots. Alright, I've gone through and circled all the trials that had 5 or 6 of the shots made. So as you look through them, you'll see that they all have one or less, 1 or 0 fours in them, because that would mean that they had otherwise, or they would have more misses than having one. Just one miss is the maximum number of misses here. So as I go through and I count them up, as I count them up, I'm going to get 28 out of 50. Should be 0.56 or 56%. So again, our simulation tells us that our 56% of the time we would expect her to make 5 or 6 out of the 6 foul shots. Alright, so go ahead and flip on over and complete your alone time, and then move on to some cotton.